Okay, here's a sample buffer system problem. What's the pH of a 0.7 molar acetic acid solution to which 0.6 molar sodium acetate has been added? The Ka is given for acetic acid, which is nice of them, and we'll compare it to this pH without the weak base. That's buffer, the conjugate base of acetic acid, without it being present. We would expect the pH without buffer to be a little lower, since buffer is a weak base. I'll show you three different ways, and I'm biased. I really like the Henderson-Hasselbalch method since I think it's direct plug-in, but let's take a look at a fast normal way to do it, Henderson-Hasselbalch way to do it, and complete ice table method. The fast way is to write down the balanced chemical equation. Note, by the way, this is called a pH of the buffer system type problem since they did not create the buffer system by a chemical reaction. Instead, they simply have the two components of the buffer system present, so it's a little simpler. Chemical reaction amounts to the dissociation of acetic acid, right, to which they've added a little extra sodium acetate. So you can say to yourself, what is the K for this? We take a generic equilibrium approach to this. It's the concentration of the products, which is hydrogen ion and acetate ion, over the reactants, which is simply acetic acid, to which they give you everything except the concentration of H+. If we're going to get pH, we need to solve for X because that is hydrogen ion concentration. We'll have to do a final step, obviously, to go from moles per liter to pH. We simply take the negative log of it. So solve for X, and it's in the area of 10 to the minus fifth. We predict the pH to be somewhere around 5. By taking the negative log, we see that the pH is 4.68. That sounds reasonable for a weak acid buffer system. The fastest method is the Henderson-Hasselbalch equation because you'll see that they give you everything, the Ka, concentration of A minus, and Ha. So we simply take the negative log of the Ka to get the pKa, and then we plug in the two numbers that they give us, and very quickly we get the exact same answer. The most complete way to do it is by an ice table method, where you write down the chemical reaction that's going on. That's an equilibrium system. You consider what you know it is initially, and there it is, what it is initially. This will go down by a value of X. This must go up by a value of X, and this must go up by the same value of X, but we end up taking two of those three and dropping them because they're going to be small, which is never particularly satisfying, but it seems reasonable since the Ka is so small to begin with. Solving for X is identical to right here, taking the negative log, just like we did before, so there's a lot of just copying and pasting right here. You get the same number. They did ask to compare this to the pH without acetate present, where this would simply be 0 right there. So this would become X, and you have an X squared over 0.7 molar. When you solve it, just like we did the other two, you get a pH of 2.45, which makes sense because it does not have any of the weak base present. So that weak base was enough to raise the pH by a couple of units. You can see right there. Okay, that's a sample problem for pH of a buffer system.